In the old war of currents between Edison and Tesla, Tesla's alternating current proved to be the winner in grid distribution. But will it prevail when it comes to local and regional distribution? The new distribution extends deeper than the power grid. It goes down into the hearts of data centers and high-performance computing. Hi, I'm ECN Editor-in-Chief David Manti. With me today is an expert panel to talk about the old war between AC and DC, the future, and what the next generation power landscape will look like. With me today is Dr. Karim Wasef, General Manager of Embedded Products at General Electric, Dr. Alex Wong, Professor of Electrical and Computer Engineering at North Carolina State University, Stephen Collier, IEEE Smart Grid Expert and Director of Smart Grid Strategies at Millsoft Utility Solutions, and Jason Dugas, the ISS Power Inverter Project Manager at NASA's Johnson Space Center. Thank you all for taking the time today.
Thank you.
Thanks for having me.
Very good. Karim, let's start out with Edison's legacy. We have seen a lot of Edison bashing, but at the core of it, didn't he just want to make DC popular?
Yeah, if you go back in time, fundamentally, Edison had the light bulb that he wanted to popularize, and to get the light bulb, he needed to get the electric grid up. From his perspective, a light bulb just needed 100 volts DC, so why would you use anything else? Now, fundamentally, the problem was that that limited the range for where electricity could work to a pretty narrow space. It really could only travel a few miles before you needed to have another station. So the solution was to go to much higher voltage. And that, frankly, was something that Edison felt was dangerous. So his concern was not so much DC versus AC. It just happened to be that with the technology at the time, AC allowed higher voltage. So high voltage AC is what worked. And his intent was to try to keep safety on the minds of people, which is why there were a lot of antics and there was a lot of, some interesting stories around what he did. But fundamentally, he was worried about high voltage being dangerous, and that was the concern. And today, there's no question that high voltage is more dangerous than low voltage. But now we know how to manage it a whole lot better. Okay. So it wasn't a DC versus AC; it was actually a high voltage concern.
Okay, Steve, what are your thoughts on this interesting twist in power history?
Well, I think he's exactly correct that everybody looking back kind of likes Tesla better than Tom. He was a nicer guy and a much more raging genius. But the fact was, Edison had this vision of relatively small power plants close to load centers. But his lieutenant, Sam Insull, pressed really hard to achieve the economies of scale and the larger utilities and larger financial models that were available through central station generation, which was unworkable at DC. You have two problems. One is the losses. The I²R losses are very high when you have to operate at a low voltage. And secondly, it's very difficult to interrupt high voltage, high current DC power. So AC prevailed primarily because of a paradigm, a industry model of these large central station power plants distant from load centers. It wasn't really if we'd had power electronics in those days, instead of having to use a motor generator set every mile or two, things might have been different.
Okay. Jason, spaceflight has used DC for a long time, but NASA recently introduced 6 Hertz on the International Space Station. Now, it doesn't get more off the grid than the ISS, but why the switch to AC?
Yeah, it's interesting what we were just talking, what someone was just discussing. I mean, it really goes back to the legacy of the AC utility, the centralized power system that we have in modern society that we've lived with up until fairly recently, and I think it's changing somewhat. But that AC system has essentially produced a situation where most consumer electronics that you buy at the store are made to plug into the wall, to your home outlet, that run off AC, even though they may actually need DC in the end application. For us, for NASA, we've been struggling with this because we have a lot of researchers and scientists that want to use the International Space Station as a research laboratory that's in microgravity. And for those researchers, it adds a lot of complexity, it adds a lot of cost, and a lot of schedule pressure to develop a DC to DC conversion system that can actually interface to our primary power system on the space station, which is DC. So what we've done is we've actually flown up some DC to AC power inverters that create the 6 hertz AC that you might find in your home or office, and that allows the scientists to more quickly and more readily utilize the ISS, the International Space Station, for the world-class microgravity research platform that it is, and we've done this in the hope that it will reduce the pressure on them from a budget and scale standpoint.
Okay. Okay. And at any time, if someone cares to interject, feel free to just jump in.
Well, let me just comment on the, if there's an example of a place where AC exists by virtue of legacy, I think, Jason, your example is pretty much there, right? It's there because the equipment that is available runs on AC. But if you were to go to the fundamentals, you're probably using solar for your energy generation, right? So you've got DC base, and most of the equipment is probably computing based, or essentially not running big motors. At least I wouldn't think so. So fundamentally, you've got AC and DC, but the legacy of AC creates this artificial space where it's a necessity. At least that's the way that I see it. Well, what's your take on it?
Well, yeah, I mean, I think that's true. The fact that NASA has historically used DC in its spaceflight applications, my feeling is that it really goes back to the fact that rotating machinery is really a problem in microgravity applications. So we've historically kind of gone towards the DC because it's easier to generate. There's less potential volumetric constraints. Things of this nature. It's just easier to do at a remote location to generate that DC as opposed to flying, synchronous machines that have rotating parts that can wear out and have reliability issues. So we have historically, in space, in aerospace applications, we've used a lot of DC. We have had some limited AC historically. 400 hertz AC power is a heritage power that's used for motors and things like that in aerospace applications. But the fact that we're flying 60 hertz into space is really a telltale that we have the equipment made by the manufacturers that's really made plugged in, and we're trying to make it easier for users to get power instead of having to design the power electronics themselves to customize DC to DC conversion.
I think that will continue to be the case for some time in the grid at large. I mean, the interesting thing is that almost a fourth of the new generation added in the United States in the last year was solar PV. It's generated at DC, then it's inverted to AC, and then it's re-rectified at the other end because the fastest growing component of load in the United States, residential, commercial, and industrial, is electronics load. And so you lose some energy, there's some mismatches, there's some reliability and failure exposure issues, but gosh, there's an awful lot of wall warts out there that you can't supply them with DC. Now we are seeing some commercial installations that are isolating their LED lights and some of their DC loads and serving them directly in what we call a micro or nano grid that's DC only. But I think both technologies are going to continue to exist in parallel for a long time, and we'll talk later about how there's some synergies between the two.
Yeah. If I can jump in a little bit, I totally agree with what Steve was saying. From a technology point of view, we inherited the AC system at that time of this inability to generate and deliver DC over long distance. So we have this huge infrastructure, so the AC system will stay for the convenience and for the existing equipment we have to support. But I think the issue is now there are two major things we're looking at is technologically we now know how to do even long distance DC, short distance DC, local DC. So the technology barrier is significantly gone for us now to look at the advantage of the DC. So the advantage is very clear by increasing the penetration of the DC distribution either at lower voltage level or higher voltage level. Because even just look at the efficiency gain, 2 to 3% if you look at the solar to supply local load. The storage system will have 3 to 4% efficiency. So we can go on alongside the advantage of full DC. So I think the issue is not who will eventually win. I think the DC, what do we see, technology, we want to see more and more of those things. And the AC will stay for a long time.
You make a very good point. You mentioned batteries. That's the other growing component of the grid. We're going to see, especially with Elon Musk now and his Gigafactory, I think we're going to see leaps and bounds in the improvement of battery storage, and that is innately a DC technology. So are fuel cells.
Absolutely, absolutely. I think uh, there are two really reasons I think go for the DC. One is energy efficiency advantage. I mean, look at the largest residential, not residential, the largest load we have now is the data center and the building load. I mean, there are numerous data citing the improvement if we go from AC-based system to a DC-based system. So the similar thing can be repeated to other load scenario. In the data center, which is the number one growing load, it probably is consume about 3% of the world energy at the moment. There is a 10 to 15% energy efficiency gain,
Yeah.
even at the load center level. We are talking about local DC distribution. We haven't even counted potential gain we're going to have if the DC advantage also apply to the distribution and transmission system. So this is the number one driver in my view. Then there are other driver which is we still have to supply the increasing amount of energy to the demand. Where do they come from? And naturally, we're looking for renewables, like Steve said, those solar and many renewable sources are in DC in nature and also local. So you want to eliminate the integration difficulties as well as make them converging more easily. So we want to increase amount of distributed generation. So that will also be a good reason to support easier integration interface, which will be a DC interface.
There's one additional energy efficiency issue with DC. The maximum amount of power that I can deliver for a given voltage via AC is 0.707 times the voltage times the current because of the waveform. I've got a lot of empty space in that waveform. For a given voltage, I can deliver more current in the same period of time with DC. It is a more energy intensive way of delivering power. That's what led to part of the problems back in the late 1800s. But now it's a problem that we can solve, and it's a more efficient way of conveying power, especially in a smaller system where I'm not delivering it over long distances.
Yeah, the ease of transformation and the ease of switching on the AC systems seems to have been a real pivotal factor in the historical aspect. One thing that I think is really interesting when you're looking at whether we'll ever kind of sway more to the DC side of things. The grid and one other panelists are probably way more qualified on this topic than I am. I'd like to hear their inputs, but the grid is an immense, maybe one of the greatest efforts in all of modern society. It was a huge undertaking built over many years, maybe 100 years or more, and how it came about and slowly developed over time. It was designed specifically for the AC waveform, and to go from that to change that infrastructure, that huge investment that society has made over so many years, to go to a DC system would be an immense financial cost and a real political hurdle to justify the switching over from the AC to DC. I'd like to know if even other panelists have any have thought about this and what their thoughts are on the topic.
So I'll speak to that because I think it's a valid point. I think once you have infrastructure, changing infrastructure is very difficult. But when you look at it fundamentally, there are already different parts of the world that have acknowledged that if you want higher energy efficiency, and fossil fuels will only last so long, and energy will become more expensive, efficiency will become a pretty strong driver. And as efficiency becomes a pretty strong driver, we're going to look at where do you begin the propagation of this migration. And I would see it happening at the loads. right? Data centers operate on DC, and so it makes a lot more sense to look at DC migration there, and then you move slowly up into the grid. The wires themselves, you can probably reuse a lot of content. Now, the stations, yeah, I agree with you. AC stations are going to be different, but the idea is how do you make a gradual transition? And the cost of energy is going to move us in the direction of one, generating power a lot more efficiently, and transmitting it a lot more efficiently, right? So we're looking at a migration that will happen. Some countries have the willpower to do it a lot earlier than others, probably because of the cost of power. But it's going to be a migration from the sources that are going to demand more efficient DC power, and then slowly migrate up the grid. At least that's my take on it.
Well, I think you make such a good point. There's another transition that's occurring that I think that's very important. For 100 years, we had large central station power plants that delivered power one way over high voltage transmission to low voltage distribution systems. What's happening now is that all of the new generation in this country is being built at the edges of the grid. It's either rooftop solar, it's combined heat and power, it's small peaking plants. And so more and more, we're using less and less of the capacity of the bulk, what we call the bulk power system. As much as 5 years ago, we were projecting huge shortages and major blackouts, but conservation and energy efficiency and distributed generation have reduced that load on the backbone system. What's happening out there at the edges, I may not need an AC line. I'm not delivering power over a long distance, and I may go DC to begin with. There's one interesting additional issue. This AC grid that we ended up with is what's called a synchronous grid. In other words, it's a patchwork of several synchronous grids in the United States. And in a synchronous grid, if I cause a disturbance on one part of the grid, all the rest of the grid senses that disturbance and may also be disturbed because it operates synchronously. If I'm operating in a DC network with today's power electronics, I can force a certain voltage, a certain VAR, a certain current flow. I can actually use DC links to stabilize the AC grid. And we're beginning to see that. It's called flexible AC transmission systems, FACS, where we use DC as a way of keeping a disturbance on one part of a synchronous AC grid from wiping the whole grid out.
I totally agree with what Korean and Steve was saying. From a business point of view, I think the natural place is start from the low voltage DC, and for me the DC-based distribution energy microgrid or nanogrid, because that's a major solution to our increasing energy demand, and gradually go up to the voltage. But I do want to emphasize what I just said earlier on. Technologically, we have the ability even to deliver, build a completely DC system today using modern power electronics technology. That's actually one of the main research we are doing, is not only look at the 380 volt level of distribution, we're looking at a 15 kV DC underground cable distribution for dense populated area like Manhattan, and 100 kV DC transmission or higher. One key technology we're looking at is called the wide bandgap semiconductor, which never available before this decade. Now we have semiconductor devices, each can handle 10 to 30 kV each. So we can build a transformer. This is one thing Edison doesn't have. We can build what we call DC transformer.
Yes.
To go to any voltage we wanted. So, but business decision, of course, is much harder, but technologically, we even have solution for that voltage. But just even take that away, just focus on 380 volt DC nanogrid for homes and microgrid for buildings. I think we have a lot to gain here. So that's, I think, from either way, we should feel very, very happy to see the future growth here.
One of the things we have to be careful of is being too myopic. The developed economies account for a quarter to a third of the population of the world. They account for 85% of all the consumption of kilowatt hours in the world. The rest of the world is going to start using a lot more electricity, a lot more electricity. China, for example, has 1/10 the per capita kilowatt hour usage that the United States does. they're going to use a lot more. They do not have a huge legacy synchronous AC grid to try to overcome. Even in India, where they have largely tried to build out a grid that looks like the developed economies grid, and in Africa there is no AC infrastructure. I think what you're talking about gets accelerated in parts of the world where these efficiencies say, well, given a choice between AC and DC, and I don't have AC already built out, I'm going to build DC.
I agree. In fact, what we see in a lot of the developing countries is that even if the grid is available, it's not very reliable.
Yes.
I think India and Africa are great examples of that. And so there's a couple of options. One of them is to essentially transport diesel to generators wherever you need them, because the grid is not reliable. And that creates a particularly large burden, right, because the infrastructure is not that great, even for manual delivery of diesel. The alternative is to have solar cells, wind, and deep discharge batteries, which actually make it a lot easier and a lot more efficient to have access to DC power, which is much more accessible in these remote areas. So when you move away from existing infrastructure in developed countries to rural areas or places where the infrastructure is not developed, DC actually has a pretty significant advantage in the fact that you don't need to run a generator, you don't need diesel. You've got sunlight and you've got wind, and it changes the dynamic of what makes technical sense right there and then.
Absolutely.
I know we are all very supportive of the DC. I think it's not to say we don't have challenges. I think there are still some technical challenges. I think some of them are perceptions, like the feel DC might be more harmful to human, but a technical lecture like this might be helpful. But there are some real things such as protection is much harder than an AC system because of the lack of zero crossing. Those are the area I think where we are coming up with solutions that can rapidly interrupt DC faults. Another thing is if you change to this plug, people familiar with a 120-volt plug, with a DC plug, you could have arc flash there because of the lack of zero crossing. Right. Therefore, we need to develop what we call arc-free plug technology. That's another thing actually we are currently developing. So those are some. I don't think it's fundamental. The fundamental is still a lot of business case has to be made. The business leader has to jump in to support more. I think there is already a trade organization called Emerge Alliance that is behind supporting DC in the buildings.
And I think one of the things that we haven't really discussed either on the DC front is just power processing. Power processing DC electrical DC currents and voltages is much more involved than, say, just throwing an old transformer in the middle of the line and transforming it from one level to the other. It's much more expensive to develop a solid, stable DC to DC conversion system that meets the needs of the users in terms of transforming the voltages down to usable levels and transforming them up if necessary to transmit them. So there's some very high costs associated with financial costs and things of this nature that have to be addressed, even though from a technical standpoint you look at efficiency and some of the other advantages that are highly regarded on the DC front. I think there's still some real issues that you're going to face when you have to process large amounts of bulk power in DC, even at the local level. I mean, for microgrid standpoint, which I know there's some folks on the line here that are experts in this area. I mean, at some point you do need that interface to the AC system. You've got to get the DC and you've got to grid tie it somehow. And the grid tied inverters are much more complicated than, say, a static, heavy, and big transformer that you just throw out there and hook up to, and things kind of just naturally work by way of Mother Nature. But the power processing aspect, I think, can't be overlooked when you're looking at a overall system cost and return on investment.
Here, why don't Kareem? Why don't you take? Oh, sorry. Hold on. Yeah, go ahead, Kareem.
Just a quick point. I think transformers are, inexpensive, and so that looks like it's very attractive. But the reality is that when you look at the efficiency, right, when you look at the value of electricity, transformers are not very good. Transformers worked really well when you had, the 1800s, and it made a lot of sense because that was the only technology that would allow you to go from high voltage to low voltage. Power electronics, and not just power electronics today, but power electronics 10 years from now and 15 years from now, the changes there are so dynamic that not just from a per unit cost, but in terms of the efficiency and the original capital investment, power electronics are making huge bounds in technology. And so looking forward at what is likely to be the most economical solution, to be honest, the most efficient UPSs today are not UPSs that necessarily have a transformer in the middle. They're actually transformerless UPSs that eliminate the most inefficient portion of the transfer process. So I agree with you that today there's a reason why we have to do it, because that's what the grid is. But going forward, not being the cheapest or the easiest up front is not necessarily what is the highest total value solution.
Kareem, I think you and I were exactly on the same wavelength, and that's why we were kind of talking over each other. The other difference is with copper and iron and Lenz's law and Faraday's law, there's only so much you can do, efficiency-wise, loss-wise, system control-wise. Power electronics is subject to Moore's law and Kurzweil's law and Wright's law. It just gets better and better and cheaper all the time. Rotating machinery doesn't. And I think we're simply going to see more and more of the world, particularly as we go, I've got to believe we go to solar and hydrogen-based fuel cells. That's a DC economy. And I think that the continuous improvement and reduction in cost of electronics will help make that occur.
Yeah, I think I probably can support Jason to some degree. For the bulk power, directly go to DC will take a much longer time, even though I spend all my time developing the medium voltage transformer using power electronics. It will still need more time to be able to replace the very cheap and reliable 60 hertz transformer. But on the low voltage side, I will say first, we already have to use power electronics for all our low voltage power delivery today. So by going to DC is not only going to make it 3 to 2 conversion less, it will make it actually even easier, because taking a step down from 380 volt to any consumer electronic device like computers to cell phones, it actually becomes much easier. So there, at that voltage level, the technology really follows what Steve was calling Moore's law, although we don't exactly have as aggressive Moore's law as a digital electronic. But there, the technology actually become better and better, even compared with today's benchmark a starting point. That's why the data center become a very good example, because we already have to use everything power electronic, even for AC system. But the bulk transmission system and distribution system, I think, will take a little longer time to see huge penetration. But I think time is now to start doing that. Yeah.
Yeah, I want to leave the impression that I'm an AC file, so to speak. But NASA has historically used DC in practically every application it got its hands on. Again, I mean, we traditionally in automobile applications, I mean, it really lends itself because the source and the load are right there together. So it's a different situation than you would see on the grid, where you need to go up to extremely high voltages for transmission purposes. So DC absolutely has a place. It has worked out extremely well thus far for vehicles. I see more DC continuing. And with the grid being AC today, we obviously have more inverter technology demand between the car and the grid, and rectifier technology going from the grid to the car. So the power electronics is astounding. The rate at which we've been able to increase efficiencies, drive down the size and the cost of low and medium power electronics assemblies is really staggering.
Yeah,
Yeah, let me add one more point on AC, just because I feel like we want to be a little bit more fair to both sides. One of the important parts about AC is that it does have a very unique property, which is zero crossing.
Yes.
Zero crossing means protection can be done so much easier. DC current has no zero crossing. It does require a much higher level of technology in order to be able to interrupt that kind of power. And that's actually the challenges that I think the rest of the panel was bringing up.
Yeah.
In addition to that, there is one other handicap that I think we need to bring up on AC, which is phasing. I think when you're talking about the
Yes.
synchronous grid, the reality is that a lot of power electronics today are dedicated to making sure that we've got phase balancing, that we've got power factor correction. There's a lot of things that happen with AC that actually create a burden that is not necessary. So it has its good points and it's got its bad points. I think technology will drive us to use the more available energy and really drive it to be as close as possible to the necessary loads with the least number of stages. And I think that's kind of the culmination, is that the least number of steps between where you generate your power and how you generate it and how you use it is really where we as a society are moving. It's minimizing the number of steps in that path.
absolutely.
College students in the power engineering schools everywhere will rejoice when they no longer have to learn symmetrical components to deal with that phasing issue.
They don't like to learn phasers. Yeah.
Yeah.
But just to support, yes, one solution to help DC system more stable or more safe is to create artificial zero crossing. So
Yes.
not like we abandon everything we learn from the AC system. We really want to eventually there may be a little bit of hybrid going on there, right? I think also the key issue is DC is already everywhere. The key discussion is, do we want to change the way we lay out our future home and building with
Yes.
availability, at least in parallel with the AC system, also a easy to plug in AC socket. That I think will be, because if we just look at today we have DC everywhere, except they're not accessible to anyone but the internal equipment. Like your computer has a DC inside, but that's not useful for anybody. What we're really talking about is we make it standards. We really need to come up with standards, and we need to come up with designs, and so maybe a hybrid solution for those. Just like the EV technology, this is for the people. For the low, that a little bit more supporting new technology. We need things going like that, and I think it's really going to be a parallel hybrid system in the future for a while, I think.
Okay. Thank you all very much. I wanted to, before we ran out of time, I wanted to launch into the Q&A. So if we could, the first question comes from Peter. Peter says, HVDC has been a proven success for decades. Why then are utilities concentrating on smart meters and the smart grid with billions and billions, but will not upgrade all long transmission lines to this technology? No more coal plants, so we can expect less plants with longer feeders. To sum it up, why are we still transmitting long distances using AC? Anyone want to raise their hand?
The principal issue there is what we've already discussed, is that the overwhelming predominance of the plant in place is AC. The cost of, you can actually use the conductor in some cases, but you can't use the end stations. And the insulation changes, it's pretty much a rip out and replace scenario, and that is a huge capital investment. I mean, one of the things that folks have been talking about with this, the increase in the frequency, duration, and severity of weather events, and the decreasing reliability of the grid itself because of age and a variety of other issues, was how do we harden the grid? Can we protect it from Al Qaeda by putting in it, burying the transmission lines, etc.? It's prohibitively expensive. I mean, a conversion of the AC grid that's in place to a comparable DC grid is out of the question. I think what does happen, though, is as we move away from the 7,000 central station power plants that have supplied all of our load forever to millions of power plants out at the edges, we have less and less need to improve, add to, replace that AC grid, and we'll see a gradual conversion to a more DC economy at the edges. But I don't see any way in the world. I absolutely agree that DC transmission, I mean, the state of Texas, I live in Austin. The Electric Reliability Council of Texas is only connected to the free world via two DC lines. And it's an artifice of a regulatory settlement that occurred 30 years ago with the SEC and the FERC and others, that an asynchronous connection was considered to be a non-regulatory connection and kept the Texas utilities out of FERC jurisdiction. So we've had DC for a long time. It works well, and it works even better than it ever has. I don't see any way we replace the existing AC grid with DC across the board.
Agreed. Totally agree.
Okay. And actually, a note to viewers out there, if we don't get to your questions here, please submit them in the comments section below, or tweet them at us with the hashtag EngineeringLive. We'll make sure that the panelists all get an opportunity to respond to your questions. The next question comes from Mark. Mark says, or asks, he didn't say it really, with low voltage, and talking about 24 or 48 volt DC installations being promoted for LED lighting and building systems from a number of eMERGE Alliance members, for example, Nextech Power Systems, where do you see the future of DC for commercial and residential power distribution heading?
I think we have.
I can take that.
Okay.
Go ahead, Alex. Go ahead, Alex.
Yeah, I think we have already hit on that topic a couple of times.
Yeah.
And 24 volt, 28 volt, those are a potential standard for the ceiling drop LED socket. And where does the 24 come from? 380 volt, which is what we call the low volt distribution voltage. A very high efficient compact DC-DC converter will be just like, or all the ballast will sit behind the socket to give you that 24 volt. So yeah, that's the technology readily available, but what needed is, of course, more of the standardization. But I think the question probably is more related to why we want that 380 volt in more general sense is I think the ability to do those microgrid or local energy generation interface as well. So you want that voltage not only get into just the building, but also outside the building, near your meters, near your panels, where you can connect plug and play, what we call plug and play solar, plug and play EV, plug and play storage devices. So you not only help with the efficiency question, but you also help with co-generation.
Yeah. I'd like to throw in one other thing on the voltage range that was mentioned. I think you mentioned 24 to 48 volts. The space shuttle, when it was still flying, had a 28 volt DC fuel cell system that ran everything practically. And those numbers weren't just made up. Those numbers have real meaning. And it turns out that voltage range that you mentioned is a much lower hazard to the human body. So it's a safety. It's also a safety issue as well. Running on at those low voltages, below that 48 volt level, you really reduce the likelihood of electric shock to the end user. So in the future, I think you're going to see a lot more low voltage than you see in the home nowadays coming out of the outlets, because it really does increase the safety posture for society in general.
Yes.
I agree. I think that's a design strategy, but fundamentally you cannot run 24 volt wiring in the house. So you have to get higher voltage towards that socket before it becomes 24 volt. Maybe it's a solution to make 24 volt available to the customer, but behind the 24 volt, you need some other voltage running your wire inside the house. But if you have the safe, what do we call it, zero crossing technology or arc-free plug technology, 380 volt will give you more ability to do higher power load. Otherwise, 24 volt is only going to be for your computer, cell phones, which I totally support. Today, actually, you can already have USB delivery line put under a table. You can plug in a USB to charge your cell phone, but those deliver very, very low power. LED probably going to stay around 24 to 48 volt. But again, there are standards we have to define how to do it.
Kareem, did you have something to add?
Yeah, I think there's a range of power for different levels of use, right? So computing operates at very, very low voltages, right? Most processors now are approaching 1 volt or below. And as you go up, you've got the 12 volt architecture for most computing applications. 24 volt is pretty standard for industrial applications. 28 volts is for a lot of wireless transmission because the semiconductors happen to operate at that voltage. 48 volts is really, really good for LEDs, depending on the level of power that you've got. And anything below 60 volts really lives in a very safe human space where it's not very dangerous. But in terms of huge amounts of power and in terms of storing a lot of energy, 48 volts is actually a pretty common infrastructure solution for a lot of energy storage with telecom batteries, etc. And so as you get up to the higher voltages, you get more efficient storage, you get more efficient use of conductors. And so I agree that really you've got a 380 volt solution that allows you to transmit and use that power over a long distance. And then in the actual application, absolutely, it's going to be stepped down to what is most usable for that application.
Okay. Let's see what Silas is asking here. Silas wants to know, is there really a new war between AC and DC? Do you have any real-life data and statistics to compare AC and DC energy transfer efficiency in grid distribution and/or local and regional distribution available?
I'd say we're in the middle of that war here in the space program. I mean, we're trying to utilize an orbiting platform that we put into space for the purpose of doing science and research. And the scientists and researchers come to us and they have a hard time interfacing to a spacecraft power system that's DC, and it's critical, okay? So when they interface to our system, we have to make sure the entire system doesn't collapse. Whereas if they have this separate secondary AC interface that they can go to, they can use the things that they can buy at the store and plug in and not have to worry about disturbing the rest of the power system. So we have a nice soft interface between to pad them. So yeah, there sort of is a conflict in some applications. And we took the efficiency hit. We just took it. We said, look, this is not the most efficient way to do things from an energy standpoint, but we're willing to expend some energy in order to gain capability and to reduce cost. So there's this balancing act that goes on, and I think it's to some extent it's going to go on here on Earth. I'll let some of the other panelists
There is not, I wouldn't say a war. I use the word challenges for DC system. We understand AC system a lot better than DC system. DC system, large scale DC system stability, small single stability, all those are things are very rich topic for more research. Data center people like the energy saving, but they still not so sure if it's really going to work if we deploy this everywhere. So every major vendor are working on not only the energy saving piece they can save very quickly, but do they know the control technology, the protection technology will really support a large deployment. But on the energy efficiency side, I cited a couple of numbers, right? The data center study of several IBM, HP data center shows 18% to 15% improvement, even in the low voltage DC distributed data center scenario. Solar will become 4% depending on how you calculate it. You probably become 4% more efficient if you deliver solar to your directly to the DC and use in the local load, versus you have to go back to the AC, come back to the local DC again. So storage, same thing. One side of the conversion you can save 2 to 4%. I mean, if you do round trip, that's significant. And so I think the numbers really add to a major motivation. So I think it should be. So it's not. So that part is very clear, but I think engineers have to provide the cost and reliable solution, cost-effective and reliable solution. That's the key.
I think Alex is exactly on the right target. It's not a war any longer. It's not a brand war like Westinghouse and GE. There is, in fact, a convergence of the two technologies that's based on a resurgence of DC for all the reasons that we've discussed. They're both going to continue to exist. It will be which is more efficient, which is more malleable, which is more adaptable, what is more controllable. I think DC's resurgence comes from three very strong foundations. The first one is so much of the new generation that we're seeing is innately DC. Solar cells, fuel cells, batteries, etc., are DC. Power electronics gets better and better and better, which makes it easier and easier and easier to use DC. And the fastest growing segment of load in both the developed countries and the undeveloped economies is electronics load, which is powered by DC. So it's going to be here. It's going to happen. And how we meld the two is based on engineering economics.
I think I don't know if it's necessarily a war the way that it was back then when it was a lot more exciting. I think it's more a question of commercial and political will to move in the direction that optimizes the power grid, right? So today, it's really a question of does it make financial sense and when does it make financial sense? Technology is already there, right? We have the ability to do it. And by the way, Edison was able to get quite a bit of DC plants and DC distribution done back in the 18th. He got up and running, but the commercial benefits of AC are really what dominated at the time. And today, the commercial benefits of DC are there, but you've got to look at how much effort it is to change a wholesale, grid. And that's not likely to happen, within a decade or maybe even a century. But there's a transition, right? There's sort of a step-by-step evolution where you begin with microcells and you begin with the right sort of locations where it makes a lot of sense for DC to establish a stronghold and then slowly build out. It's not going to be a war where one of them is going to win in 10 years. It's not going to be that kind of war.
Okay. Well, we are running out of time, so I just wanted to close with this question, and I mean, I'd like to end with the war. That's fantastic. But I'd like to just run down the line, starting with Steve. Are you an Edison or a Tesla guy, personally?
What do you side with?
Well, I really like Elon Musk, and I think Nikola Tesla was a lot like Elon Musk. I think there's some significance in their car being called the Tesla. I think Tesla was a visionary, revolutionary. Edison was an inventor. He was an engineer. He was a perfecter. And so I don't think they're necessarily directly comparable. Edison would take a known technology and perfect it. Tesla would come up with a new idea. So I like them both. You need the guys that perfect the technology, but I guess if I had to pick one or the other, I would pick Nikola Tesla as a visionary, but I think DC is coming back.
Okay. Jason?
Well, Tesla is sort of the in thing to say these days, and and for great reason. I mean, he was an unmitigated genius, in every way. I actually like Edison quite a bit because of his cut and try method. He didn't always know the theory behind what he was doing, but he had an amazing sense of tenacity. He was, absolutely unstoppable. He got it in his mind that he wanted to accomplish the number of filaments that he tried to get the light bulb to work. I mean, you can go on and on about how he just didn't let anything stop him. So I'm an Edison guy in some respects. I still love Tesla coils, and we actually have a project going on here at NASA Johnson Space Center where we're doing work with wireless power transfer, which goes all the way back to Tesla's work. So I like them both. I'll vote for Edison this time.
Alex, Edison or Tesla?
Okay, I will give you maybe short answer. I would think I really admire and envy what the Tesla's AC system has really done for us. One of the major engineering marvels of our last 100 years. But I think he's lucky, of course, developing the Poly system, and that really was a valuable and economical technology. So, but I also like Edison because he didn't finish the work, so we can now do what he has started. Now we have the technology to bypass that advantage of the polyphase system. Maybe using high frequency conversion, we can go from any DC voltage to any DC voltage. So both of these guys are really great guys and inventors. I'm an inventor. I'm engineers. I also want to be a visionary. So I want to predict the DC will take slowly to replace more and more. One thing that hasn't been said is this distributed generation, what is the end game? I also say a market transformation is needed. In order to reach a market transformation, we not only need a more energy efficient grid, but also we need a little bit more resilience in the grid. Steve has touched upon how much resilience is needed. So it will reach the point where the DC grid is the only one I think will give us this asynchronization and plug and play at any level. So we can have all nano grid and microgrid participating in the energy market transactions. That is really a long term. To do that, you have to have grid is so flexible, so controllable, and stable. So we can allow plugging and dispatch of energy at any time, and the rest of the energy can respond quickly to supply the difference in demands. So that's what we call the basically what we call the you can call digital energy era or energy internet scenario. But you need a grid that shouldn't be so strongly coupled electrically like today.
Kareem, I'd like to end with you. Edison or Tesla?
So I think it's a question of when, right? Back then, I think Tesla had the right answer for the time. I would like to imagine that if Tesla existed today, if he was alive today, he would be so excited about what power electronics could do that he would be focused on how to make DC the most popular and the most efficient solution possible. So, being GE, I have to say Edison because he was a visionary in seeing DC. But I'd say that if Tesla was here today, he would be the strongest proponent of Edison's DC solution.
Yes, I agree. Absolutely.
Electronics.
Definitely.
Well, thank you all very much for taking the time to be a part of the panel. I'd like to thank all the viewers out there for submitting questions. Please continue submitting them in the comments section. We will get to them after the event. Thank you all very much. It was a very fruitful conversation, and I hope to do it soon again.
Thank you.
Thank you.
Thank you.